here we continue to discuss inviscid flows and derived a first form of Bernoulli's equation, which is the most general Bernoulli equation. We'll discuss in the second quarter another case where we can impose the Bernoulli equation, which is more restrictive. So this is the weaker form, but it is the more general form because we don't require extra assumptions, which we'll discuss later, which is irrotationality. So this is a more general form. All right, so in the inertial regime, the Navier-Stokes equation reduced to the Euler equation. And so when we write the Euler equation, we essentially assume that, the flow is incompressible, right? We're assuming that. And we assume the effect of viscosity to be negligible. Now for the Bernoulli equation, we will make a few additional assumptions. We'll assume that the flow is unsteady, so this term will drop out. Sorry, I meant to say the flow is steady. So this term here will drop out. We'll assume that the body force term, so I already wrote it in a term, because most of the time we'll see the body forces as a gravity force. But it could be not just gravity force, but we will assume that if it's not just gravity force, then that the body force is a conservative force. And that means that F derives from a potential. I'll call the force potential, I'll call it phi. And the last assumption that we'll make is we'll assume that the flow is, not just incompressible, but that actually the fluid has a constant density. Now here, I'm assuming a constant density because this simplifies slightly the formulas. You don't strictly need the density to be constant. To use Bernoulli's equation, you can assume more generally that if the density is only a function of the pressure, that is, if you have a barotropic flow, then you can also derive Bernoulli's equation, but it's simpler to derive for constant density, and it's very rare that we will have density a function of pressure in examples that we use in the IFD. So you can find a more general derivation in the book. So this is not strictly necessary. In chapter 4.9, you can find a more general derivation for barotropic flows, and these are flows for which the density is only a function of pressure. But we will not do that in this class. Okay, so let's derive the Bernoulli equation, and for this we start from the momentum equation. If we assume that the flow is steady, then the momentum equation is the following. And so here we can use a mathematical formula which is going to help us to project the momentum equation along a streamline. So this formula you don't have to know, but it turns out that U grad U is equal to the cross product between the velocity field and the curl of the velocity field plus the gradient of the norm of the velocity squared divided by 2. Right, this is just one of these mathematical formulas from differential geometry. But this formula allows me to rewrite the momentum equation. Now, this is my momentum equation here. I'll keep this term on the left-hand side, and I'll move this term to the right-hand side, and I'm moving these two terms on the left-hand side, and this then yields, so we have rho times the gradient of the norm squared of the velocity divided by 2, but we assume the density to be constant, therefore I'm just going to put the density here, plus the gradient of P plus the gradient of our force potential is equal to this vector here. And note that this vector here is the curl of the velocity vector times is the cross product between the velocity vector and another vector. In that case, the curl, but that doesn't really matter so much. You know that when you're taking a vector cross another vector, this vector here is normal to the vector u. So if I call t a unit vector in the direction of the local velocity vector, we can project this equation on t. So if we're taking this equation here and we project it on t, the right-hand side is going to be equal to 0 because because this vector here, which is normal to t, dot t will be equal to 0. And therefore we're left with t dot, note that here on the left-hand side, we have the gradient of three functions, so we can write it as the gradient of the sum of these three functions. And that is equal to 0. If we assume that the body forces are gravity forces, then the potential is rho gz. And now you may recall our discussion when we first discussed the total differentials, that if you project the gradient of a function onto a particular direction, that is what is called the directional derivative. Right? This corresponds to the rate of change of this function as you move not along the x or the y or the z direction, but as you move along the t direction. So the change of this function in the t direction. And so note that what this equation tells us is that this function does not change in the t direction, and therefore that this function here is constant if we're moving along the t direction. And one other way to say that is that this function, p plus 1/2 of rho u squared plus the force potential, has to be constant along a streamline. And that here is the weak form of the Bernoulli equation. You can always make this statement of momentum conservation. Here, this is a statement of momentum conservation because it comes from the momentum equation, that p plus 1/2 rho u squared plus v is equal to a constant along a streamline if you have an incompressible inviscid flow. So if we assume the effect of viscosity to be negligible, if the flow is steady, if the body forces are conservative, and of course if you can follow a streamline. Right? When you cannot follow a streamline, that will be an indication that there are effects of viscosity, because that would suggest that there is unsteadiness and mixing in the flow. Right? So as long as you can follow a streamline and that the flow is inviscid, incompressible, and steady, then you can always use Bernoulli's equation to look at the relationship between the velocity and the pressure. And I think Bernoulli's equation you've seen before, so that's an equation that you are familiar with.